Okay. So we want to prove the left side equals 2. In a lot of cases, I will actually replace this equal sign with an arrow. Because what I don't want you to get this idea in your mind that you can do whatever the heck you want with this. I want you starting from the left side and moving to the right side. Because some of you will get the bright idea, oh, well, you know, once I get common denominators, I'll just cross multiply. Not working, folks. You're proving that the left side equals 2. So I will, in a lot of cases, replace that equal sign with an arrow so that you understand you're moving from the left to the right. Okay, so I see that we have 2 fractions and they don't have the same denominator. So what do we need to find because we're subtracting them? Common denominators, right? Do you have to find common denominators when you are multiplying fractions together? No, you do not. Thank you. But you do when you add or subtract fractions. Does x minus 1 have anything in common with x plus 1? Answer, no. You need to understand that x minus 1 and x plus 1 are completely different. Okay? Just because there's a letter that looks the same inside of them, that does not mean the factors have anything in common. It's kind of like we're dealing with a 2 and a 3. They have nothing in common. So what are you forced to do if you had a denominator of a 2 and a 3? You'd have to multiply them together, right? Same thing's happening here. We have to multiply them together. So, ooh, interesting. Wait just a doggone second. I see some, well, we could go down this road two ways. We could get common denominators, but there's something easier here, isn't there? What was your suggestion? Could you factor that? Ooh, there might be some canceling out going on here. Whoa, this might be easier than we thought. So what does that thing in the red factor into? X plus 1, x minus 1. That's nice. And I'm going to guess the same thing's happening over here, right? What's canceling out on in the first fraction? Ah, the x minus 1's leaving me just plain old x plus 1. And what's canceling out for the green one on the right? The x plus 1's. Do not be the kid who says this. Oh, the x's cancel out and the 1's cancel out. Okay. That's killing me, folks. The quantity x plus 1 is what canceled out. Okay, what I just said was highly illegal with the x's and the 1's. Okay. So, oops, I should use green again. So that leaves me with x minus 1. What goes in the middle? Ah, yes, the good old minus. Now, why did I put those purple parentheses around that second one? I do have to distribute that negative to both. If I do not distribute that negative to both, we're in trouble. So that negative gets distributed to both of those. All right. So I got x plus 1 minus x plus 1. Anything cancel out? Ah, the x's. All right. Heading back to Texas. Leaving me 1 plus 1, which is 2. We did it! We proved that the left side equals 2. Now, could we have gone about doing the whole common denominator thing? Yes. But we would have created more work for ourselves than we needed. And as soon as we saw that, oh, hey, we could factor those numerators and start canceling stuff out, much better way to go. Okay. So we are going from the left side to the right side. Here's what I need you to understand when you're doing these. There are lots of ways to go. I can replace cotangent with 1 over tangent. That may or may not be helpful. I could replace cotangent with cosine over sine. That might be helpful. Now, how am I going to know which way to go? Whether I want to do 1 over, maybe I want to take that tangent, make it 1 over cotangent. I'll tell you what you should look for. Over here should give you clues. So even though I'm starting on the left and I'm moving to the right, you use this as a guide to help you think through, what should I replace this with? So since this is based on secants, which we know that's 1 over cosine and that's 1 over sine, what do you think I should replace those with? I need the sines and the cosines, don't I? Okay, so that's what we're going to do first. Yes, you would be looking back at your notes, or on a test, you'd be looking at your formula sheet, and you'd be saying things to me like, oh yeah, let's replace that with sine over cosine. I need to zoom in. My fingers are just too big for this. Sine over cosine plus cosine over sine. Okay, those are definitely not the same denominators, so I can't add these fractions until I do what? Get a common denominator, right? So, what do I have to multiply the first fraction by? Sine x, right? Okay, and what am I going to multiply the second one by? Cosine x. I heard you. This stuff's pretty easy. Nice job. I hope it is, and I hope it stays that way. That's right. That's right. Whew, man. Some of these can be easy. And I will say this. As they get more difficult, I'm not going to throw the hardest ones I can find at you on a test. For crying out loud, they would take forever, and you possibly could get really lost. I've watched math teachers, including myself, start to go down the path of some of these that get more difficult. And because there are multiple ways you could substitute, they substitute things that start to get real ugly real fast. And I have caught myself and went, this can't be that hard. And I have had to go back and redo the problem. Some of them are simple. You're right. So what is sine x times sine x more commonly referred to on the street as? Sine squared x. And what about cosine x times cosine x? Cosine squared x. Of course, the denominator is still sine x cosine x. Please tell me that you're seeing some super cool magic right here. That's going to be 1, right? Pythagorean identities, sine squared plus cosine squared equals 1. Now, I need to remind you of something. Can you tell me what 1/2 times 1/3 is? You guys know that's 1/6, right? Is that the same thing as 1 over 2 times 3? Okay. So in my next step, is anybody freaking out if I separate it into two fractions that are multiplied times each other like this? Just making sure that that's not like, earth-shattering stuff. All we're doing is taking those two fractions, we're just, bloop, cell mitosis. Is that mitosis? The one? So? Okay. Tell me, have we got it figured out so far? I don't want to go too fast. Some of these things are, we want to make sure that we walk before we run. So what's 1 over sine x? Or do you have a question about this so far? Okay, so what's 1 over sine x? Cosecant x. Cosecant x. And then what is 1 over cosine x? Secant x. Are we done? Are we there yet? Did we get to our destination? Does the order matter? Is 2 times 3 the same thing as 3 times 2? Yeah. We're done. We got it. Yeah. Was her name-o? Okay. Or his. Not sure. Okay, I wanted to make sure we did examples 1 and 2. You'll start with example 3 in the video for tonight. And now, back to our regularly scheduled program, how to help the students with your 5-1 homework. Because you had to do 1 through 61, so are there other ones that you need help with? 61? Oh, where is 61? Ooh.
I mean, there's not really that much. I can do that. Plus, I don't
61 looks weird. What's going on with 61 here? Let me use my other writing tool. Okay. Cosine of sine x equals 1. So 61, so x is an angle. Okay, there's some ugly evil going on in 61 that I think we need to avoid. Quite honestly. I think we're going to forego that one. Well, all right. Let's see what we can do with this. Okay, so how do we get rid of... How do we get rid of cosine? How do we get rid of cosine? Don't say we divide by cosine, because that's not true. Cosine inverse. Suppose we take the cosine inverse of both sides of this equation. So you got your cosine, you got your sine. Yeah, this problem won't be on your test, by the way. Cosine inverse of 1. All right, so cool stuff happens there. So sine x, cosine inverse 1. Cosine inverse. What is the cos? First of all, you got to remember the range of the inverse cosine function. What is the range of the inverse cosine function? Shall I remind you?
Hey.
Range of the inverse cosine?
0
to pi, thank you very much. So cosine inverse of 1 is going to spit out an answer between 0 and pi. Is that 1 an x value, a y value, or a slope? That's an x value. So where on your circle do you have, and you can only answer between 0 and pi, where do you have an x value of a positive 1? X value. Right over here at the edge of the circle at 0, right? So this side turns into 0. Okay, now you tell me. Every angle measurement you can think of on the circle that has a sine of 0. And we can even think, yes, you're completely right. We can even think about the sine wave, right? We can think about this thing that's doing this forever and ever and ever and ever and ever, right? And ever and ever and ever and ever and ever. Sorry. Too many evers. Typing this to a friend, that's cool. So y equals 0, running right through there. It hits it a lot, doesn't it? Can you describe to me all the times, besides the one kid who already did? Can you tell me any of the answers? Pi? Yeah, pi's right here. It's right there. Pi over 4? No, pi over 4 is like right about here. That doesn't look like one of the intersections. 0? Yeah. 2 pi? 3 pi? See, on the circle, folks, remember, y values are here. So y value 0, y value pi, 2 pi, 3 pi. You keep hitting 0 for the y values. So whether you're looking at the circle or the wave, you can see there's a lot of them, right? How would you describe all of them? It does say find all of them. And that's a pretty doggone big word right there. I know it's only 3 letters. But we're talking about the entire real number line, right? So it happens a lot. You named a bunch of them. How do you name all of them? Integer multiples of pi? Sure, we said stuff like this. N pi, where n is an element of the integers. You know what? I should give doggone extra credit for people who can actually listen to me and use that kind of notation. I had nobody write that down. They were just all writing down things like, where n is an integer. I'm like, yeah, okay, all right, I'll let it go. Just slightly offense, but it's the red pen of death cannot really do anything about it. Okay? So, I might just do that for the people who go above and beyond. That's 61. Yeah, that was a little weird. I'm not going to be throwing that one at you. The other ones are fair game, especially those quadratics where you have to factor them. Those are fair game. What else do we want to go over? Things that you were working on in homework? So I guess I should probably go back and change that assignment to just 50. What? 23. So, good news that people watched the video. If you did and you're still having problems, that's okay. Why is this not? I said clear all drawing. Oh, because it marked it on that. Oh. Got to be smarter than what you're working with. You really do. 23. Hopefully you did watch, all of you guys watched the videos to help you with problems. When you still get stuck, I understand. Because these are not the easiest of things in the world. Ooh, I bet we can substitute that with something. That's cotangent. Ooh, okay. All right. So we got cotangent x, cosecant x. Ooh, wait a sec. Can we do a little bit of reducing right there? Can we get rid of one of the cosecants? Yeah. Makes my life easier. Hopefully yours too. That's not as simple as it can get. We can do more. What do you think we should do to get that into something where you might start seeing more stuff cancel out or reduce? Yes. Let's switch them into sines and cosines, because then we might start seeing some cool stuff happen. So what's cotangent? That is cosine over sine. Now, instead of writing it vertically, I'm going to write it horizontally. Divided by, and what are we going to substitute in there for cosecant x? 1 over sine x, right? I've noticed over the years that when you start writing things vertically, if you had cosine x over sine x divided by 1 over sine x, people get lost. Although, I'll show you a cute little trick that you might want to need to use in your future. Especially, you might see it show up on SAT, which might speed things up for you. But what are we going to do with this? Multiply by the reciprocal, thank you very much. And anything cancel out. The signs do. So we're left with the simplest version of the entire thing, which is cosine. Now, for those of you who like to keep things vertically, if you have the same denominator in the top and the same denominator in the bottom, you can do that little trick right there. And then you just have cosine divided by 1. Same thing as cosine. So you can do it either way. But if you really are not understanding it, you might want to write it horizontally and then just realize that you're multiplying by the reciprocal. A lot of you do real well thinking through that process. Okay, what else did you watch a video for and still got confused about? Anything else from 5-1 you watched a video on and got confused? 26? Okay. Oops. Let's clear that off. Okay, 26. Wow. What are you seeing right here? I hope you're seeing that's a 1. I made that easy. All right, now do you want to do a substitution for secant squared, or do you want to do a substitution for tangent squared? You take your pick. Probably both. Oh, I don't know. Let's see here. I'm going to go back to my Pythagorean identity, which you have to know. Cosine squared u plus sine squared u. I'll just use u's for kicks and giggles. Just so it's consistent. If I want secant squared, what am I going to divide by to make that turn into a secant squared? Cosine squared. Yep. Okay, so that means I divide that by cosine squared, and I divide that by cosine squared. So secant squared is equal to what? What's cosine squared over cosine squared? 1. And sine squared over cosine squared? Tangent squared. So if we're going to replace secant squared, it's going to get replaced with 1 plus tangent squared. And then, of course, we have this minus tangent squared. Anything canceling out? tan squareds, right? So what's the answer to my question? 1. If you go to the resource room and you start asking a math teacher to work these out, generally they get really giddy, if you understand the terminology, because the nerdy side of every math teacher comes out when we see these things, because we love these things, man. It's just a puzzle. It's a puzzle to take this and substitute here, and watch it simplify. I know you think we're weird. Okay, anything else through 61 odds that you have been working on, that you watched a video for and got stuck still in understanding? Okay, so we should jump to 5-2 and find some practice problems to work on from the first couple examples, as somebody types all these notes to a friend. Okay, cool. Let's start with number 1. Prove the algebraic identity by starting with the left-hand side. That's what LHS stands for. I know, technical stuff here. Supplying a sequence of equivalent expressions that ends with the right-hand side. Okay, that's where I talk about using the arrow instead of the equal sign, so people don't get all creative in the way that they're doing this. So where do you think we should begin? Should we FOIL? Oh, that's not a bad thought. So, yeah, probably going to FOIL here. I don't think it's a bad idea to go right here and do what? On this left fraction here. Factor out an x squared. Okay, so right now in your notes, because you're doing question 1 with, everybody's doing it. I know, this is GCF right there we can pull out, and we can FOIL that stuff together. Work with each other, talk to each other. Think about factoring out your x squared right there, FOILing that together. This is not bad done. Okay, if you take an x out of the top, which is what we're going to do, we're going to see that you can't take one x out of the top that would cancel with that denominator. Yes. So that's a good thing. Okay. So if we take an x squared out, that would leave us with what? X minus 1, right? And of course, you got an x in the denominator there. Anything canceling out? One of the x's, right? Right here, one of the x's. What if, instead of taking out x squared, what if I only took out an x? Because I knew that was going to happen. So instead of taking out the full GCF, I took out only the part that would get eliminated. So what would this fraction turn into if I did that? X squared minus x. Okay, so x squared minus x. Yeah, that should be x squared minus x, not minus 1. Good catch. Nicely said. And then what did you get when you foiled all that stuff together? Negative. Oh, did you distribute the -1 already? Whoever said that? You took care of this? So that's something people need to pay attention to, because if you just foiled what's in the box, you would get x squared minus 1. The key there that somebody just suggested to us was that we distribute that. And so we would have x squared minus x squared plus 1. All right, now what? The x squareds cancel out, and we're left with negative x plus 1. Are these two things the same? Yep. They're trying to be all tricky because they reversed it. Yeah, we're not falling for that. We know better than that. Okay, jump down to question 3. Jump down to question 3. Factor those numerators, look for stuff to cancel. Factor those numerators, look for stuff to cancel. See, they're starting you off with algebra 2. And eventually this is all going to change into trig functions. We're just kind of taking you down memory lane here.
I'm so bad.
You did it well.
Not really, but I appreciate it. X squared minus 4, x squared minus 9. Factor those two numerators and see what cancels. Okay, now, in between those parentheses, well, what's in between? What's in between is you got rid of the x minus 2's. So x plus 2 here, the actual minus. Yeah. That's the part that you miss. You miss that minus sign that you carry down there. You got x minus 2, x plus 2. X minus 3, x plus 3. And then look for what new ones. I don't know. Did I ask you what
You said that wrong. I said 2.
I distribute the negatives.
Not yet.
Did you end up getting it to work?
Yeah.
Did I have? Prove if you did. Minus -3. Now, I know what's going on here. The second row is going to my bad here.
We don't need that section.
Started playing like classical and you're sure one show.
Okay. So we have x plus 2, x minus 2 over x minus 2 minus x plus 3, x minus 3 all over x plus 3. Okay, so a lot of you were showing me that you got rid of the x minus 2's. So that left you with x plus 2 on the left side, minus, and then over here you got rid of the x plus 3's, and that left you with x minus 3, and then you could distribute the negative x plus 2 minus x plus 3. And so you ended up with those dropping out and getting 5. So lots of you did well on that. In questions 5 through 10, the answer is either going to be sine x or it isn't. You have to figure out whether they're equal to sine x or not. You have to show your work, okay? So that ain't just that easy. So go to question 5. Start working it out to see if it equals sine x or not. Did you follow that over there? Did you follow my logic of how we factored it and canceled? Okay. Go to question 5. Start working it out. I'll cut that part of the video. I'm not that dumb. No. Sometimes. Oh, yeah? Bloopers?
Highly entertaining.
All the times he thought it.
So what'd you replace the numerator with?
1.
1. Amen to that. Okay. So you ended up with something that looked kind of like this, right? I replaced the cosecant x with 1 over sine x. The big question is, does that thing at the end equal sine x? 1's cancel out. That's so cute. All right, now. Just, you know what? You could say that because it's true. Just don't say it at a party, okay? 1 over 1 cancels out. Okay, I'm telling you, the bullies of the math world are going to pick on you. And I don't want that to happen. Okay, so changing it from division to multiplication, what do we do with the second fraction? Flip it. Is 1 times sine x equal to sine x? I hope so. Seriously. Of course it is equal to sine x. Okay, so that one did work. All right, go to question 7. Go to question 7. Why? Because the last one did?
Yeah.
But there was a question in between.
What are you going to replace cotangent with? Is it going to be 1 over tangent, or are you going to replace it with cosine over sine? Probably cosine over sine, right? Because we're looking to see if anything cancels out. Is this one going to end up giving me sine x? It is not going to equal sine x. Right? Because we ended up with cosine squared x over sine x. Now, for those of you who think, oh, cosine squared, what could I substitute that with? Could we substitute that with 1 minus sine squared? That's part of that Pythagorean identity? Yes, we could. But you're going to find as you continue, even if you split that into 2 fractions, that you would get 1 over sine x, also known on the street as cosecant x, minus sine x. It's still not equal to sine x. So it wouldn't work. Wouldn't make anything any better. Yes, go eat food.